Good afternoon, everyone. Welcome to our Unicorn PhD Postdoc Club. My name is Teresa Leonhardt, and I'm the leader of the Unicorn Club, and I have the great pleasure to introduce our club to you, to people who, for example, haven't been to any of our previous events. So, in our club, we organize various science communication events, such as lectures that we call Deep Mind lectures, that are usually on some not very well-known topics throughout UCT, or they are on topics that are actually even studied at UCT, and are sort of introductory 101 courses into the following events we have, such as this PhD Postdoc Club. So today at the PhD Postdoc Club, we will be talking about chemistry and computers. We have very special guests today. Although the club is called PhD Postdoc Club, we have, I think, the youngest guy talking at the PhD Postdoc Club ever. Then we have one of the members of Unicorn Club talking, and then perhaps one of the oldest guys talking at the PhD Postdoc Club ever. I have also noticed that two of our speakers are playing guitar, so maybe they can make a band after our today's events. We will see. So a little more about what our plans are. We are also leading the Craft Club, which is a sort of tinkering event for anyone who wants to join. Next week on the 19th, we are having PC assembling workshop. I think it's already full, but we have opened a few more places. So check back in your email, the invitation is there, and try to click the link again if you're interested in assembling a PC with us. On the whole UCT events, such as Lesamai, etc., we usually have our booth as well. So come visit us there. Today we have a PhD postdoc that we have called Chemistry plus Computers equals Best Friends Forever, because we thought that it would be really nice to introduce this phenomena to a broader audience. I myself was actually surprised how many groups there are at UCT that actually deal with computational chemistry. So I'm really pleased we had the lecture last time that introduced us to the world of computers in chemistry and computing, and today we will be looking at these people who will tell us a little more about various practical aspects of the computing in chemistry, what they do themselves in their labs, what they did for their theses, etc. So first I would like to introduce Jakub Ježek. Please come here, Jakub. Jakub is a third-year student, a bachelor from the lab of Professor David Sedmidubski, and he explores how computational chemistry helps design better materials. And in his talk, he will show how scientists use quantum calculations and density functional theory to peer into the atomic world, and why choosing the right approximation can make or break the result. So, Jakub, the floor is yours. Please take the microphone After Jakub gives us his talk, there will be a short time for questions. Since we are recording the lecture, I would like you, if you have a question, I will bring you this microphone so that your voice gets recorded for the recording. Also, I would like to ask you to stay after all the lectures are finished, because the highlight of the PhD Postdoc Club is the delicious food and drinks that we have ready here for you. So please stay afterwards for some meet and greet. So, Jakub, the floor is yours.
Thank you so much for the introduction. So, ladies and gentlemen, thank you all for coming. My name is Jakub Ježek, and I will be saying a few words about solid-state quantum computations and why is it different from molecular approach. My thesis supervisor is Professor David Sedmidubský, and I also work at Physics Department of Czech Academy of Science. Sometimes I also go to the lab and I see people who do very interesting stuff, but basically usually they are developing some new materials, and new materials require niche conditions when they are stable. Sometimes it requires high temperatures. You need to do a lot of engineering when it comes to your apparatus, or you have to optimize the composition of your compound, or sometimes you also include some precious metals, so it's also kind of costly. But when you have to do a lot of samples, it's kind of good to have some piece of information that tells you which material would overcome the previous one, so that you can do new, better semiconductors, or better some detectors or anything. First, I will deep into some basic theoretical background, but don't worry, it's not that complicated, and at least there will be some cute pictures of some orbitals and so on. Then there will be some basic principles we usually use, and I think that these principles are kind of general that you could see them also in your field probably. And then some examples of what's usually type of results I get from my computations. First, we usually deal with crystals, and crystals have a periodic structure, and we can use it. We actually know this electronic structure that have the same periodicity as our crystal. So symmetry is very convenient in this case. But what's also usually happening when we include some heavy metals or heavy elements in general, the electronic structure is very delocalized. So the probability of finding some electron in the interstitial space around the atoms is non-zero, and we have to include that, and then to find the correct energies for this kind of quantum state is kind of difficult. To describe what's happening with the electronic structure, we have to use wave functions. Wave function is just a mathematical description what an electron is doing in the spatial coordinates and also time. But when you have a norm of this function and square it, you get distribution where the electron is located. unfortunately, when you do all the physics, you find out that only one electron functions are fully solvable analytically. So only hydrogen atom is 100% correct, and when you want to include heavier elements, you have to do some approximations. But why? When you have two or more electrons, you are dealing with a three-body problem. That basically means that you have three or more bodies or elements that are particles that are interacting with each other somehow, and you can't analytically describe their behavior. So you don't know what is happening in time equals infinity. And even a slight change of coordinates or velocities can lead to very different outcomes. In this case, the right case is really different, even when both cases at the beginning were almost identical. How are we dealing with this problem? We don't use wave functions. That's a big approximation, but when we don't have three particles, we have hundreds of particles in our systems. So we are looking at the electronic system as a whole. And we define electron density. We use density functional theorem, and it's this sum. But other problem we have to tackle a lot of times is that when you only do some organic compounds, you usually do, for example, compounds with carbon, nitrogen, oxygen, and these are light. But when you want to include some heavy elements, you have to also think of their velocities, that they are relativistic, and you have to include relativistic effects of your electronic system. And it also is a big challenge to calculate it correctly. But when it comes to the general principle, how the calculation works, you start with some physics equations, and you describe it using a functional. Functional is a mathematical apparatus that you put an electron density into it, and you get energy, or total energy of your system. The problem is that you don't know the functional, and you don't know the electron density. So you do some iterative algorithm, and you change parameters of your functional. And there is a theorem called Hohenberg-Kohn theorem that tells you that if you converge it with this iterative algorithm, you achieve energy of your ground state. But how this energy is calculated? It's basically these three terms. First, it's some kinetic energy of non-interacting electron gas. Then this Coulomb energy. Both these terms look complicated, but in fact they are computable. So a good computer can calculate it in, sometimes it's minutes, sometimes it's hours, sometimes it's days or weeks. But this is computable. But then when we also did this approximation, one was the electron density, that we summed up our one electron functions, and then it was also the exchange. We didn't include that the electrons can exchange with each other because they are they are the same. And this term is not possible to calculate correctly in density functional theorem, and you have to approximate it. It's done, for example, by LDA. That's just a table that tells you in what value of electron density you get this value of exchange correlation energy. But it's a big approximation. It's also possible to calculate it more correctly, or it's not still correct, but it requires more computational force. For example, this hybrid functional, or also double hybrid functionals are also the case, but the computational demand is very high. Other approximation you do is that your potential of your electronic system is their mathematical description is very, very weird, and you don't want to do integration on this complicated thing. So you substitute it with some linear combination of these plane waves. These plane waves are the same periodicity of as your crystal, and you can do like many of these. And when you have enough plane waves, you get the same potential basically. But what's an big problem that you need a lot of these. The potential looks like, as in the picture, around the atoms it's really steep, and in the interstitial space it's really shallow. That means that you need really thousands of plane waves to describe it correctly. So, another approximation. There are two approaches. One is called muffin-tin approximation, because the potential looks like tin for baking muffins. And you just say, okay, this is my muffin tin that's around the atom, and here I describe it like this, and I deal with the interstitial space completely separately. And then I do some math and sew it together. The second approach is I create a pseudo function that describes well the interstitial space, and separately I also do the atomic like orbitals, and I sum it up. Now I will present one of my recent results, and I will show you what was actual contribution for my colleagues who did that. My colleagues were developing new neutron detector. In neutron detector, you need some material that absorbs neutron rays and converts it into visible light, because visible light is normally detectable, for example, by photomultiplier. But they wanted, into this garnet structure, they wanted to include scandium. But in theory, scandium could go into the site where gadolinium lies, but also in where aluminum lies. And that was the problem. And it didn't do as well as they expected. And they wanted to know why is it happening. They had an assumption that in scandium, in this gadolinium site, it creates some traps, and it's slowing down our excited electrons. But they wanted to prove it, and they wanted to know how to fix it. So first we did some structures. We edited some atoms in the of the structure and optimized its structure to achieve lower energy that at the start to get the real structure, and then calculate another final calculation where the results were density of states and total energies mostly. This is what density of states looks like. It tells you the y-axis is energy and the x-axis is density of states, and it basically tells you in what energy region you get this probability of finding an electron in this particular state. And you see that it's some semiconductor with some gap. The lower part is occupied by electrons. The higher part is not occupied by electrons. But what's actually visible that these states that are green probably were doing these traps where the excited electrons were slowed down. And then we tried to get rid of these traps to find thermodynamical conditions where a structure without these traps is present. And because we had total energies, we could substitute a linear combination of total energies of oxides we also calculated, and we got enthalpy of formation. And when you get enthalpies, you also find some other thermodynamic data, and you get a Turner phase diagram. And in fact, you find some region of stability of this Garnet phase, and you can analyze where the defect is present and where not. And that's all for my presentation. Thank you all for coming, and if you have any questions, please ask. Thank you.
So, any questions? If not, I will start. I want to ask, maybe you will not know, but my question is, you said that you are working on the crystal, right? Because it has some kind of periodicity. How I imagine it is, you need a few molecules of that thing to make the crystal, and then after some amount of molecules, the lattice will repeat. Right?
What was presented was one elementary cell of the crystal, and if you have this elementary cell, then it's being repeated in.
Yes. Do you know what is like the maximum mass of the elementary unit? Is there
sometimes
any?
the elementary units are not known, because when you also include some dopant, you are not sure if this dopant is homogeneous or if it's clustering or something. But in fact, we usually use what's periodic, and when we include the dopant, we put it into some particular site, but we can't be 100% sure that it's true, because there are unlimited ways to put this dopant in.
Mm-hmm. So there isn't like any sort of rule that would state like if the basic elements that compose my molecule are this many and this size, the one cell will be big like that, or is there any like natural rule to that?
Maybe we are talking about different things. These inorganic crystals are not composed of molecules. There are also molecular crystals exist that you have different types of molecules and they consist a crystal together with this usually it's done not by covalent bonds but weaker types of bonds. But this is full like crystal, for example, I don't know, sodium chloride, and you can 100% be sure that this sodium chloride is this elementary cell is cubic, and it's with this composition.
But for more complex structures, it's not possible to get this like knowledge.
Yeah, it's possible.
It's
it's being done by, for example, X-ray diffraction. You just put X-ray on the crystal, and you can see how the X-rays are behaving in the crystal, and tell the periodicity of your crystal and the atom positions.
Okay, thank you. Any more questions?
How did you get those cool phase diagrams?
How you get these cool phase diagrams? You start with a lot of data, like a lot of data. Mostly experimental, but sometimes it's also difficult to find a good type of data. For example, entropies of formations, they can't decide if it's negative or positive. And then you have some program, Calfat or FactSage or something, and the construction like this is really quick, but you have to put it into some database, and then you optimize some parameters you don't know for sure, and also you have to include some solid solutions sometimes, or some different types of approximation, because not everything is known about the system. And then you get these binary or ternary diagrams.
So it's based on computational data basically?
Yeah.
Okay. Any more questions? If you have no questions now, it's fine. You can join us for the meet and greet after and ask in person. Okay, Jakub. Thank you. So our next speaker will be Věra Šrenková. She is also a member of the Unicorn Club and helps us organize these events. Besides that, she also helps to organize Vědátor live streams, and since she has almost finished with her PhD, she works as a science communicator at the Academy of Sciences. So today she will tell us about polarized light and computations revealing 3D structures in solutions and solids. Her PhD was done at the Institute of Organic Chemistry and Biochemistry, and her work combines polarized Raman spectroscopy with computational methods. So the floor is yours.
Okay, thank you for the introduction. So as was said, I combine experiments and computations, so I am not very good at either one. just a joke. And first I wanted to start off with what is actually polarized light. So I prepared this nice video for you. So what you can see if you look at this beetle through right lens of glasses for 3D cinema, they are completely dark, and if you look through the left lens, they are very colorful. And it's because of polarized light, because these beetles, they reflect circular polarization, left circular polarization preferentially, because of these helical structures that are in their cuticles made out of chitin, and that's why we can see them only on our left eye, because the staircase of chitin molecules is winded to the left. So polarized light is more sensitive to internal structure than unpolarized light. And it can manifest differently. It can be absorption of molecule of circular polarization, it can be reflection, it can be also inelastic scattering. So in my work I use inelastic Raman scattering. So photons have some frequency, they scatter it, and there is a change in that frequency that I detect. And there can be various methodologies that I can use like this. For example, this linearly polarized Raman spectroscopy, LPRS. I shine with light which is naturally linearly polarized from the laser already, and I can, for example, detect only scattered light which will be in the same plane, or I can, for example, detect light that will be perpendicular to the incident polarization plane, or I can be completely rotating it and see how the intensity changes, and it gives me some information about the sample. So I can also use circular polarization in my experiments. So, for example, in this circularly polarized Raman spectroscopy, I am using light of defined helicity, and I will detect only scattered photons that have the same helicity or contra-rotating helicity. And there will be some change in the intensity of the bands. And these two, LPRS and CPRS, any molecule can be scattering like this. It's also very symmetry dependent, and they have some different applications. In my work, also use this Raman optical activity, which is defined basically, it can be defined the same way as CPRS, but only chiral molecules will scatter, only chiral molecules will give me this signal. And it's good if I want to know some secondary or tertiary structure of biomolecules in water solutions. So in my dissertation, I was focused on conformational studies. I started off with four-modal nucleotides, and I wanted to see how they wiggle in solution, what their conformation is. And it's a work that combined both computations and experiments, and we also developed some new algorithm to see what the conformer populations are, because common force fields that are used for molecular dynamics are they are not working good for nucleotides. I also did some method development. So originally, we have this Raman microscope in the basement that originally used unpolarized light. And my boss came to me and he was like, we want to make Raman optical activity on this microscope. So I tried and it didn't work. But accidentally I did this linearly polarized and circularly polarized Raman, and also circularly polarized luminescence on the way. So we can use this methodology now. And I was also focused on solid state. So this is a drug named sofosbuvir, which is used to treat hepatitis C. And it can exist in 3 different polymorphic forms, in 3 different crystallite forms. And I pressed them in tablets, and I was using linearly and circularly polarized Raman together with computations to see if this method, which is basically very sensitive to symmetry and point, which is very sensitive to symmetry. I wanted to see if it can differentiate the polymorphic forms better than unpolarized Raman. And then finally, linear polarization, it's very sensitive to crystallographic Miller planes. So I had this drug called indomethacin that was milled to different crystallite sizes. And I was scanning across the sample, and I was trying to see there is something weird about the dissolution profiles with this drug. So maybe it's not just because of the sizes, but maybe there may be some factor that the crystallite planes, they may be orienting differently in different sizes. So that's what I was doing. I will only discuss here this Raman optical activity and this drug polymorphism. So first, I will start with conformational Raman optical activity study on model nucleotides, and I was doing it because nucleotides, they are still used as a novel therapeutic drugs. But deconformation, it's very diverse. So there are 4 dihedral angles that can describe their conformation. They can wiggle a lot, basically. There's this glycosidic bond which can rotate. It can be in anti or syn conformation if the base is towards the sugar. There can be different sugar puckering, or there can be different backbone torsion of the phosphate residue. And what you normally do when you want to simulate Raman optical activity spectra is you start with molecular dynamics. And from this, you see how the molecule wiggles. Then you sample some solvated geometries because Raman optical activity is very sensitive to solvation. And then you calculate the spectra, and they can look like this. This is ensemble of like 700 spectra. Normally, you would just average them, you would get this line, and you would compare it to the experiment. But it just does not work. And why? We tried different molecular dynamic force fields. And we tried DNA, RNA, we tried protein, and the general force fields that are designated to small molecules, but all of them were causing this artificial hydrogen bonding. You see this, can you see this D1? Like oxygen phosphate is hydrogen bonded to the sugar hydroxyl. And it's completely artificial. It does not exist. So there is a sampling bias from the molecular dynamics. And what we did is this algorithm that kind of sweeps the problem under the rug. So we suppose that experimental spectrum is a linear combination of calculated spectra, but the calculated spectra, there are some biases. For example, this conformation will be highly preferential over other conformations because of the flaw of the molecular force field. So we suppose it's a linear combination, and these coefficients, they are unknown, but they depend on a Boltzmann factor somehow. But what we don't know is this free energy surface. So we try to find it by minimization of this function. Also, molecular dynamics is basically skewing the conformation towards conformations that do not much exist. So we wanted to start off by creating a regular grid. So these are calculated spectra. Now it's regular, and now we can compute how the free energy surface looks like, and we can make some probability map, which will tell us what the relative conformer population is. So based on molecular dynamics and experiments, we are now able to tell what conformers are present in the solutions of the nucleotides. For example, before this guanosine monophosphate, our molecular dynamics, it was saying there is almost no syn conformer of the glycosidic bond. Now it's more populated than before. And of course, the same for thymidine citidine monophosphate. And of course, the computed spectra are much better than before. So there is improved spectral similarity index. And we were also able to tell where the signal is coming from. So in Raman spectroscopy, you calculate polarizability derivatives. And if you set those derivatives to 0 to certain atoms, you can get signal from just the base or just the sugar and so on. And this is what the picture is saying to us. So this top one is Raman spectra and contributions to total Raman signal, which is black. You can see that most of the signal is coming from base and sugar. When it's coupled, it's a very strong signal. And despite the fact that the base is planar, it contributes also a lot through glycosidic bond and through sugar-base coupling to Raman optical activity signal in water. Does it make sense? A bit? No? Now let's move on to solid state. So drug polymorphism of this antiviral drug, sofosbuvir. So the idea behind this was I have this derivative of nucleotide, and it can exist in like 15 polymorphs, but we were focusing on this form 1, form 7, form 6. Form 6 is what you find in the commercial product. It's the most stable, it's the most compact, so it has high density. And it also exists in this high symmetry space group. But form 1, if you look at the single molecule, it's very conformationally different from form 7 and form 6, right? And form 7 and form 6, they are conformational similar. The molecule is almost the same, but there are parallel chains, and here are anti-parallel chains. And my idea was, if I try these polarization-sensitive techniques to different symmetry space groups, will it somehow differ? Will it give me more information? So that's what I did. This is the spectrometer, or the microscope that we have in basement. It's a Raman microscope. And I can insert various wave plates here in the incident path, or here in the scattering path of the microscope, and I can manipulate it at my will. So let's start off with unpolarized spectra. If we look to the left, this is low frequency Raman region. It's experiment. And basically, low frequency region, it should be telling me something about the crystal packing and about hydrogen bonding, because it's very sensitive to this. And form 1, it's very different from form 6 and form 7. This is what I wanted to say. Also, the fingerprint region here on the right, the only difference here is only this CN, CO stretching and NH deformation. In form 1 is more different from form 6 and form 7, which are basically indistinguishable. And I use, of course, some DFT computations. So this is our cluster that we have in IOCB. It's called Aurum. And I start off with X-ray diffraction structure, and I propagate it in XYZ direction. I get this huge crystal, which is not possible to compute itself. So we do a little trick that we extracted these dimers, these unique pairs. And for these pairs, we calculate polarizability derivatives and other derivatives that I want to. And I compute it in Cartesian coordinates, and then I computed it in internal coordinates, and then I transfer it back to the huge crystal. So finally, I am able to have a nice spectrum for this 3,500 atomic crystal. And I use 3 different approaches. Basically, I don't know if I can go into details, but I can optimize this cell in plane waves. Then I can propagate it, then I can extract the unique pairs, blah, blah, blah. Or I can just leave it as it is, propagate it, then I optimize these unique pairs only, transfer it back to crystal, and obtain the spectrum. Or I can do both. I can optimize this in plane waves, then I propagate it, and then I optimize it again. It's important because I want to have the spectra computed as on the same level of theory as is the optimization. So that's why it matters. Comparison of computations. So here on this slide, I just wanted to say that if I obtain a spectrum of the 0 phonon mode, it's better. It's as if I had the spectrum of one cell that it's propagated in infinite directions, surrounded by its twins. So that's better. It also looks nicely with comparison with experiment in the low frequency region. So, but we chose to continue with this model. And here is comparison of experimental on the top and computed linearly polarized spectra. Here low frequency, here fingerprint and CH stretching region. And I just wanted to say here that this form 6, it has higher symmetry, so there will be differences in, they just have 2 times better discriminations power for, so let me start over. So form 6 is in higher symmetry space group, and we do a trick by computing so-called depolarization ratio, which is ratio of this blue one to red one. And overall, this form has higher symmetry space group and higher depolarization ratio, so that's why we are able to distinguish the polymorphs better. Hope it makes sense. With CPRS, circularly polarized Raman spectra, it's even better. We do not rely only on intensities and position of bands. We also rely on the shape of bands. They are also bisignet. There can be sign flipping of the forms, and it allows us for a 3 times better discrimination between form 6 and form 7. As I mentioned, they are very similar. And to conclude, Raman optical activity is indeed very sensitive to molecular conformations, but right now it doesn't exist in microscopy form, and there is also no solid state way to, there is also no way to probe solid state. Our new algorithm allows for correct extraction of conformer populations, and it can be used also for other molecules where the molecular dynamic force field is not right, for example, for glycoproteins and other stuff, and simulated spectra corresponded well to experiments. Also, for example, if we have in pharmaceutical production this Raman microscope, my point is if we upgrade it with polarization optics, it can make the resolution much better, especially if we include quarter wave plates to produce helically resolved light. Simulated spectra reproduce the trends. However, the signal must be properly averaged because there is anisotropy because of the crystals. Okay. Thank you for your attention.
Thank you, Vera, for the very nice talk. So, are there any questions from the public?
Thank you for your presentation. I would like to ask about the method you tested, and was it also effective for different types of compounds, or because I would think that this would be good also in general for different molecules.
What method are you talking about?
Like how you did the gridding, and you found what conformers are present in the structure.
Mm-hmm. So it might work well for conformers from molecular dynamics, for which I have already computed the spectra. It might also work for conformers based on regular Gaussian. If I have Gaussian and do conformational sampling, create a grid, it might also work. I just need to have a regular grid. But there is also a negative to this method that if you saw, I had only two dihedral angles. And for example, the sugar puckering is described by 4 of them.
Mm-hmm.
So.
Yeah, so the grid would be 4-dimensional. Yeah. Thank you.
Okay. Any other questions? So maybe I have a question. So the machine is called a Raman microscope. Mm-hmm. So does it take any pictures or does
It
it only
does.
take the spectra?
It does take pictures, but in fact those are pictures where in every pixel I have one spectrum, so they are not a picture per se, but I can reconstruct the picture based on chemical information, based on the spectrum.
So what is the resolution of, like how big object can you observe?
It's a regular confocal microscope, and the resolution depends on the diffraction limit. So it depends on the wavelength I use. What else does it? And on the objective, of course.
So the
Numerical
resolution
aperture.
would be like somewhere 200 nanometers around that, like visible light
I
or
don't
UV light, or
remember the
even
formula
lower?
right now, sorry.
Okay, no problem. Okay, any more questions? No, if not now, just stay for the refreshments and you can ask Vera later. Okay, thank you, Vera. And now I would like to introduce our last guest, our final speaker, Václav Hanžl. He is a PhD student in Professor Spivak's group at the biochemistry department. And interestingly, after years spent in speech recognition and language processing, he now explores the usage of artificial intelligence in the world of proteins. So he will tell us a little bit about what AlphaFold does or does not do. Thank you.
Thank you. Good evening, ladies and gentlemen. It's my big pleasure to be able to speak here as a PhD student again. It's true, I'm a second-year PhD student because Professor Spivak is a nice person and is willing to take some adventure, and I'm willing as well. So that's what's happening. I'm also working with Dan's fossil. It's other side of the same coin, as we will see very shortly. I will start with something seemingly unrelated. If you've never seen this before, it's a collapsible carrot. You can have a look. Interested? It can be used to make people smile. It usually works as a nice icebreaker. And the other thing is evil cube. You can put it out of the box, then into pieces, and you will never put it back to the box. It's the exact opposite. It usually makes people extremely unhappy. And what they have in common is, of course, that they are 3D printed, and 3D printer can do mostly anything, including parts of itself, and it can do it at scale. This is how Mr. Prusha is making 3D printers on 3D printers. Whatever is orange is part of 3D printer, either being printed or being used in the printer itself. So if we compare it with nature, it does something very similar. While Mr. Prusha, if you can see my laser system, it does that shape layer by layer, making outline, then tracing what's inside. Nature does it with ribosome and somehow magically gets 3D shape as well. And if we compare the scale, nature is much better in doing it at scale than Mr. Prusha, even though he is quite good one. And both nature and Mr. Prusha say it's very good for innovation. If you need new shapes, this way you can get them very quickly. And this is how we got here to this room after some 4 billion of years of iterations. If we look inside, on the left side, it's how it's encoded. Well, it doesn't show anything. It encodes X, Y, Z. This is the movement in space. Sometimes there is E, or always, mostly always there is E. It's how much plastic to extrude from that printing head. Sometimes there is color change, but it's not that often. But it has X, Y, Z coordinates in it. If you look at the nature code on the right-hand side, it's just 20 different materials being swapped. No X, Y, Z. It somehow magically happens that it has the right shape quite often. So that's the interesting part. And this is how the nature have chosen to have the choice of materials. Some of them are plus charged, minus charged. They might attract each other later on, forming part of the 3D structure. Some of them are hydrophobic on the left side. They will also touch each other later on, being attracted by water pushing them together. Some of them, or one of them is cysteine, which will cause connection with other cysteine, stabilizing the structure maybe later on. So this is part of the 3D magic. If we look at it in detail, on the left it's one tiny part, mostly alpha helix, with side chains. We often do it on pictures without side chains to make it clear it's in the middle, but it still is not very clean, so we make the slightly artistic picture on the right, drawing nice helix while there is actually none, or there is, but it's a bit imaginary, stabilized by hydrogen bonds. If we look at it at scale, on the left, this is how it looks like. On the right, it's our slightly artistic, scientific notion how we draw it in articles to convey any information at all. And in fact, 3D shape is on the left because all those atoms have some radius which can't be entered by others. So altogether it makes some 3D shape like in the 3D printer. And it can actually get quite large and quite messy, and we would like to be able to predict structure like this one just from the sequence of amino acids, because we know nature somehow magically does it to build a structure. Even if we look at the structure in our symbolic way, it's not very clean. You can know that there are some even RNA parts in it, not only protein. If you like programming analogies, you can imagine that protein code as Python and RNA is some humble C code which is helping this to happen. If you look how ribosome works, most of the interesting parts are done in RNA, like Python itself is made in C, maybe C++, C. So why do we care at all about protein structure? It's a nice game, it's a nice topic for PhD. My PhD is about protein dynamics, moving protein structures. Well, the reason is obvious. We can find ways how to break what the protein does by sticking in small molecule like small grain of sand in clockwork and stopping its function and breaking it, and then we can sell this molecule as drug. People don't want to be ill or don't want to die even, so they will buy our drugs, and indirectly their money will somehow make our PhD lives possible, doing interesting things, going through grants, states, taxes maybe, etc., etc. So it's not totally true that we just break what it does. About half of the drugs on the market are protein inhibitors, which really stop it doing what it normally does. From the rest, about half is sort of questionable whether to call it breaking the function. Imagine you break the ATM machine and it will give you more money than it should. So I would still call it breaking. That's another half of the remaining half, protein doing more than they should, and the rest does something else. When we count it by number of pills, protein inhibitors will be vast majority because the simplest, most common drugs are protein inhibitors. On the other hand, if we count it by money spent, breaking proteins will not be majority anymore because new expensive drugs, mostly antibodies and related things, are rather based on protein-protein interactions and similar things. But we are still in the similar domain, but it's not breaking by small molecule. So people got interested in protein structures to make money or to make science or to make people not die, and they gradually collected quite huge database of structures, protein database. Initially it was a very complicated game of making protein crystallized, that's those crystals mentioned before. You take proteins which never crystallize in normal life, mostly. Then you mix it with all the strange things you have in your lab, and then maybe magically next day or next year it might crystallize or not, and you make your PhD or not, and another entry to PDB. That's it. Later, nuclear magnetic resonance with its own ways of being crazy, like you need a really strong magnetic field, you have to cool it by helium, etc. It's expensive, it's complicated, and yeah, but it's starting to fill PDB as well. There are other techniques today. So all this made gradually possible to try the magic nature does. You have a sequence, you somehow convert it to folded protein, and after many years of mostly failing, one day at CASP14 AlphaFold 2 made that known breakthrough, being like 3 times better than anybody else, and computer folding became a method comparable with X-ray, NMR, and other experimental methods, getting somehow to the same rank of precision. For me personally, it got interesting when OpenFold repeated what AlphaFold 2 did, making it fully open source, including training code. That time I noticed maybe it's not just Google with another electricity bill for $100,000, maybe it's a clever model. And yes, it is. It's extremely clever model. I did AI models all my life. I was starring in I don't know, excitement at design of AlphaFold 2. It's really clever. It has like 5 things in AI models never done before. And at the same time, it's relatively small. You can run it on your gaming machine, which I immediately did, and play with it. It's nice. It's wonderful. Well, this is how it's structured. Just very shortly, the structure of AlphaFold 2 and OpenFold is exactly the same, only OpenFold is made in PyTorch, which programmers like, while AlphaFold 2 was made in some other toolbox Google likes, unlike most programmers, I think. And you give it multiple sequence alignments, which is sequences of sort of similar proteins. You give it templates of those which are similar, which can be found in PDB, and most of all, you give it the sequence itself, and whatever you give it, it combines somehow together, giving you the structure at the end, and it's a very good one compared to anything computer predicted before. So I told everybody, hey, that's so clever, there should be Nobel Prize for artificial intelligence. Unfortunately, there is none. There is not even one for mathematics. You probably know that false story that Mr. Nobel had some problem with his wife and some mathematician. It's a nice story, but it's not a true one. But they made it, they call it physics and chemistry. It was actually artificial intelligence. That chemistry actually uses protein language models. That's how I got here, because I knew language models. I decided, hey, if I find some nice person who would take care of me, maybe I could learn some biochemistry and do PhD. I already know the most complicated tools. Now maybe I could learn the simple things. So that's what I'm doing at the moment. And yeah, so at that time, everybody noticed. There is a little problem with artificial intelligence. It does exactly what you ask for during training. You ask, hey, this is my training data, learn on it to do something. It does. And surprisingly, quite often you wanted something else. You just was not able to express yourself clearly enough to say, I want that. And that's exactly what people noticed with AlphaFold 2, that, yeah, we can get new structures as if PDB contained them, but it's not what we wanted. We wanted our structure to which we can fit our small molecule. Maybe the structure is moving, the molecule will fit into different conformation than the one which would be in the crystal, should that crystal be in PDB, should the protein ever crystallize. And also, people noticed we would like to have more training data. Nobody is going to make another PDB anytime soon. It was 50 years of very hard work. So one magic which can solve that is called pre-training. You somehow get a lot of data, like the text of internet, all the languages, all the text ever put on the internet by anybody, or alternatively, you go with a bucket to some sewage, get it out, do DNA sequences of everything you find, and somehow you don't know what it means, but you can use it in pre-training. And that pre-training method is actually very old. It's originated as a way to, you can try to fill in what's missing. In the meantime, while I explain, it originated as a method to measure whether newspaper article is readable or not. And if you manage to guess the words, it's readable. If you did not manage, it's not. And it's exactly how artificial intelligence can be pre-trained. You get texts, you only drop some words and ask it to fill them back. You know what should be there. So you have your training labels, and somehow the task is actually pretty complicated. You have to understand the language. You have to understand proteins. You have to understand speech to be able to fill in missing pieces, and that's what gets encoded in BERT, ESM, or Hubert, or maybe Uber, maybe it's French model, used in different domains of artificial intelligence. So there is another way which is used in BERT. Tell me whether those two sentences follow each other in the original text. This is another way how to get training data without actually doing any manual labeling and force the model to get some higher understanding of the language. But this is just a little fine-tuning. There is ISM model or ESM3 also, which do sort of similar principle for proteins. So let's have a look how the structure which can fill in the missing words actually looks like. It's based on attention mechanism, and if you look at the sentence in the bottom, you can imagine amino acid sequence as well. It's the same principle. Each layer is paying attention at different words in lower layer and somehow making those initially similar words like bear and bear to be distant at upper layers. And if you look at the representations of those individual words or amino acids in the upper layers, actually that one rectangle is like 1,000 of numbers, and they magically encode not only identity of the word or amino acid, but the whole context, maybe meaning of the sentence in which it happens, relation to other words, etc. And for proteins, somehow these representations know a lot about structure before you show it any single structure from PDB. And that's quite a big magic. And the same magic happens with language. Bert already knows a lot about language before you ever ask it to translate between two languages, explain jokes, or do whatever you need. This is just fine pre-training, fine-tuning at the end. And apart from saving us manual labeling of everything, it has another magic influence that we do not train on our final small objective at the end. We train on a general knowledge of the language. And we have much better chance that we will get what we want, because the final fine-tuning doesn't take us that seriously. It has its own general knowledge of the subject. Yes, this time specialized to what we asked for, but it generally knows much more than what we asked for in fine-tuning. So we have good chance that it knows things we even didn't ask for yet. This is how it's done mathematically. What's interesting is, if you was here last week, it's done with big, dense matrices. That's exactly where it gets easy with current hardware and GPUs. Attention is just matrix multiplication. So if we compare with AlphaFold structure, instead of MSA, multiple sequence alignment, which is quite hard to find, it can take like an hour to search databases. You can compute language model in seconds. Also, structure database is not searched for, and structure module is simplified. It gets sort of similar results to AlphaFold 2, slightly worse for ESM-fold. There is another use of this in OpenFold, which is not leaving out evoformer. This is, in my experience, slightly better than original AlphaFold 2, especially for things which are somehow out of the box. If you play with proteins, try to design new ones, language models are your friends because they knew before everything before you asked for structures. And somehow they know structures, but they know much more. They just don't reveal that. So, one question might be, why don't we just use molecular dynamics for all that? Yeah, we can simulate all this. Well, the short answer is we can't. It takes too long. Whatever we do with AlphaFold would take many years to do with molecular dynamics. Just a little bit, because it makes nice picture. If you put protein in molecular dynamics, you need much more than that. You need some kitchen salt at least around. That's those balls around. You need some water, those other smaller things. And it's problematic because it's too big, so you do tricks like circular space you've seen before. You know it from old computer games. When you have a spaceship, it goes to the right, it reappears from the left, and if it disappears down and reappears up, this is what molecular dynamics used to get sort of infinite space. And if you look at that ion which is in yellow, it's somewhere, it's jumping to the opposite side. This is exactly what that space does. And it's a good way to verify that small molecule will stay at place. You can simulate your 200 nanoseconds in one day, but it's not way to start with it. Actually, you want your sort of separate sciences of small molecules and big molecules, and you want to merge them together. If you ask those scientists what's their preferred tool, The left one will say random forest, the right one will say transformers attention. And the interesting part is that you need, of course, both of these things to be able to design any drug. You need protein to put it in, you need that small molecule. If you use random forest on proteins or transformers on small molecules, it does something, but it's not exactly easy, not exactly the right tool. So the next generation tried to capture everything in one tool. AlphaFold 3 can do cofolding, small molecule and protein. AlphaFold 3 can also do RNA and DNA together with it. There are many free implementations of AlphaFold 3. Boltz 2 would be probably the most prominent one, and it added quite interesting innovations on its own, like molecular dynamics generated training data. That's another way how to deal with the fact that nobody is able to repeat PDB amount of data anytime soon. We can simulate some of them. Ligand affinity predictions, that's a really interesting part because there are many ways how to measure that small molecule would like to stay in place, where it's breaking things. There are things like EC50 and different constants which mean totally different things. Boltz 2 was able to use them all in one training, just taking each data set sort of comparatively knowing if EC50 of this molecule is bigger than that one. Somehow their affinity should be in the same order when I compute how the molecule stays bound. So they were able in quite creative way to use whatever is found in really fragmented chemical databases to be able to use it in one unified training. That's quite an achievement. And Boltz 2 is getting to the limit when small molecules are not totally described by a random forest area only. It's sort of entering that transformer space. It's very shy in that space yet, but it's coming. Diffusion models are another innovation which is used in many things, but in AlphaFold 3 as well. That's another way how to deal with the fact that you don't have enough training data, you want to be lazy in labeling. Here, if you want to generate many images of cats, you just take any pictures of cat or drawings of cat, whatever, and you just ask people, hey, write me short text label cat. And then you train your network on artificially noisy images. You take your picture of cat, you add some noise, and you train your network, hey, this is my noisy cat, this is my text string, what I want, cat, make me nicer cat. And this way, generated images can happen, and you just change noise at the input, you get different cat on the output, because on the left side there is nothing left from the original cat. But each of those 1, 2, 3 neural network is able to make it more cat-like until you get one cat from one noise or one protein structure from one noise. This is how AlphaFold 3 is trying to get you some diversity without much success to getting real diversity. Boltz 2 is slightly better in this. This is still not the whole picture. As I said, proteins are moving. And they take different shapes, AlphaFlow, ESM flow, or BioEmu are explicitly trying to capture that movement. Simple fold is interesting one because it can also be forced this way, and it's the first one which can run on your laptop, should it be from Apple. And ESM fold also somehow knows about diversity. It just doesn't tell you in normal training and usage procedure, but it knows because it was pre-trained on those unlabeled tons of data. It can be fine-tuned to do many things. And this is little example how we play with it. This is a pump which can be made moving, and it's better seen if you look at it at the top. We can actually make it open by reading some subconscious ideas ESM-Fold has in its language model. We do it by adding some artificial noise to attention heads, and it reveals that it had other ideas how the structure could look. It can be potentially useful in drug design, because if we want to block a pump like this, we don't know in which conformation actually it would stick. We want to try them all. We want to predict all conformations. And protein design is of course hidden in all this, because I was speaking about analysis, but any analysis can be used for design. If you sort of randomly design and then verify by analysis, hey, maybe it does what I want. So you can do by random increments or some more directed mutations of what you do and finally get what you want. Some tools are going very explicit in this direction. Boltzmann is the latest and greatest. David Baker got Nobel Prize quite some time ago for some initial designs in this area, and we are really again in the area where protein design is like 3D printing. You design it, you get it in the shape you want. And it's also interesting if you want to follow money. That's area of those newest drugs for rich people who don't want to die, and will give you your money for some special drug, and later on maybe it will become some quite normal drug for normal people. So let's have a look at it with some scientific interest. Protein design is of course part of drug design and will be more and more. And that's all from me today. Thank you for your attention.
Thank you, Václav, for the talk. So are there any questions? Anyone?
Thank you for your presentation. I would like to ask, the data the models are trained on is like from 50 years, but still we can say that some of the data was measured a little bit wrong or something. If there is like 10 structures and one of it is wrong, does it involve does it make a difference when you learn the AI on it?
Sure. Yeah. Basically, garbage in, garbage out. I always wanted to do AI and leave data filtering to my students one day when I was working on speech. This never happened because data filtering is by far the most important part. So 90% of your time you spend by sifting out what should not be used in training. Making smaller data set can give you much better results if you do it right. At the end, you can be pretty sure a lot of nonsense was left in your data, and maybe you can still redo it later. Your models are quite helpful in verifying your data set. It's actually quite normal in speech or protein design or wherever that you use your model to control what is really nonsense in input data, or maybe you even use it to augment your training data, because your predicted data might be even good training data, surprisingly. So yes, you are totally right. Errors in training data are a big problem. You try to avoid it as much as you can. At the end, the artificial intelligence have to keep, even with input data which are not perfect, it somehow does. But if you filter it right, you get better results, it's sure.
Mm-hmm. Thank you.
Any more questions? So maybe I have one small question. I have actually many questions, but we can leave it for later. So there at the end, you have shown that the model can predict that how the protein can move a little bit, so that it like opens a cavity or something like that. So is it also possible if I have a simple molecule, can it then like design the protein around it? For example, if my original experimental data would show that the small molecule does not react with the protein or does not react very well, can the model tell me, okay, change this part to make the large protein fit with the small molecule?
Yeah, I think we are getting there. That's the latest wave of design tools trying to be productive exactly that way. If you want to, let's say, catalyze even some reaction, it might try to put the critical residua around the reaction site exactly the right way, then stabilize them by other parts of the protein in the right structure. So yes, we are getting there.
But it's not something that's like publicly accessible yet, I guess, or
I think
in
it
the
is.
way that, for example, I'm not sure if those programs are still relevant, but there was like Rosetta or Fire or those before AlphaFold folding models
Still being
that
developed
even
in-
like laymen could use without extensive programming skills. So are these molecular dynamic tools available in this way without programmatical knowledge, for example?
I'm not exactly playing with protein design tools, so maybe others like Mr. Spivak could answer questions like that because he is. I think it's getting to the same level as protein analysis. So I didn't personally play with that, but I'm pretty sure there are free tools you can use for protein design at the moment, even if they were not with slightly more, but not that much programming effort. You can use analysis tool by randomly mutating what you have, looking whether it's getting better or worse. But I think if you look at Tamarind Bio, you will find some protein design tool by today, I guess. And this is extremely easy platform. If you would like to try something new and don't want to learn anything, if you make account on something like Tamarind Bio, and there will be more tools online. There is always nice default setup of everything, and you give it your sequence and your smiles, and it does something, even if it's not the greatest things with the default settings. Even if it doesn't have some protein design tools at the very moment, it will have next month. But my guess would be it has.
Okay, thank you. Any more questions?
Earlier, you mentioned that the newest drugs are usually using the protein-protein bonding instead of the foldings. So, is there like a reason? Is it like somehow superior, and if it's this, what's the reason we are still looking for the way to fold the proteins instead of trying to look into this direction?
Well, it's the proportion is certainly growing of new drugs which are not being small molecule protein inhibitors. At least money-wise, the proportion is growing. These things are problematic because small molecules, you can usually eat them in a pill, and if it's well-chosen small molecule, it will somehow get to the right place after some time. With bigger molecules, you usually have to inject them somewhere because they will not survive being eaten. So it's getting important. It's not the only new drug. Small molecules are still being searched for, maybe much more than before. It is quite normal to start with screening of extremely huge spaces of theoretically possible small molecules, do computer pre-filtering before you ever get to to the lab. So this is still happening as well on quite a huge scale. It's just that another branch of big molecules and protein-protein interaction, or maybe RNA-protein interaction, is getting important. It will probably get more and more important as we are getting more information about RNA. It used to be a sort of a side player. People said, hey, there is DNA, some part of it is coding proteins, the rest is some junk. Whenever somebody tells you this is a junk which is doing nothing, usually he is totally wrong, and that junk is doing some really important stuff, like those glia cells in brain, which are not neurons. They used to be called, hey, this is maybe some glue keeping neurons. Today they got much more important roles in recent research. So RNA is exactly that type. It's growing from, hey, there is maybe also some RNA, to, hey, maybe we are mostly made of RNA doing everything with proteins for some side functions, and DNA as well. So we can expect RNA drugs more and more. COVID vaccination was based on RNA. It's a neat trick. If you can inject RNA and let the cell synthesize something, you can also use RNA as directly as enzyme, or directly as antibody, as aptamer. So yeah, that's growing. It's not as easy as small molecules. It's maybe easier from a legal point of view. In small molecule space, many things are already patented by somebody, or maybe already published. It's not easy to get money for testing of small molecule. You may say that big pharma is getting big money and they don't want to make this small molecule, but because before the small molecule gets to the market, you have to actually verify that it will not kill people instead of curing them, and it costs extreme amount of money if you can't patent that small molecule to make sure you will make some money on it. Later on, you probably will never try to verify that it's a safe one. So that all somehow opens those new areas, but by far they are not that dominant. They are dominant money-wise.
So it's solving like different ways, and if we can solve it through the small molecule, it's easier to use the small molecule. But if not, we try to find the other ways.
If we can do it through small molecule, we generally like it. We just take a pill from the shelf and eat it. That's what we do daily.
Okay, thank you.
Okay, any more questions from up here? No, maybe not. Maybe not right now, but everyone is very welcome to ask Václav later on during the meet and greet. So thank you, Václav, for your lecture. And thus our PhD postdoc club concludes, and everyone is very welcome to join us for the food. I thought much more people would be coming, so there is a lot, so please don't be shy. Stay here, grab some snack. Thank you.